Hello friends, I am Muhammad Azhar Iqbal Navalgund, Assistant Professor, Department of Physics, Government First Grade College, Mundarki. Today we are going to discuss about the Norton's theorem. In the previous class we have studied the basic terms and definitions of electronics, Kirchhoff's current law, Kirchhoff's voltage law, sign conventions, voltage source, current source, and the Thevenin's theorem statement and proof, and the procedure steps to find the Thevenin's theorem. Now, today we will discuss the Norton's theorem. The statement of the Norton's theorem is any two-terminal linear network containing sources of EMFs and impedances or resistances can be replaced by a constant current source in parallel with a single impedance or resistance. The current is equal to that current which would pass in a short circuit placed between the terminals, and the parallel impedance or resistance is equal to the impedance or resistance between the terminals when all the internal sources of EMFs are replaced by their internal resistances. The simple circuit is like this: a EMF, resistance R1, resistance R2, and a load resistance RL, and the two terminals A and B. The equivalent circuit of this circuit is a constant current source, a equivalent resistance connected in parallel with the current source, two terminals A and B, and a load resistance. Here VAB is equal to I divided by 1 by Rn plus 1 by Rl, where Rn is the equivalent Norton's resistance between A and B. I is the short circuit current between A and B. Now see the proof of the Norton's statement. Here is the simple circuit diagram. Here we have two mesh or loops, E R1 R2 E and A RL B R2 A. Applying Kirchhoff's law to the mesh E R1 R2 E. Minus of I1 into bracket R small r plus R1 bracket complete, minus of bracket I1 minus IL bracket complete R2 plus E is equal to 0, or I1 into bracket small r plus R1 plus of bracket I1 minus IL bracket complete R2 minus of E is equal to 0, or I1 into bracket small r plus R1 plus R2 minus of IL R2 is equal to 0 is equal to E. Question number 1. Applying Kirchhoff's law to the mesh A RL B R2 A. Minus of IL RL plus of I1 minus IL bracket complete into R2 is equal to 0, or IL RL minus of bracket I1 minus IL bracket complete R2 is equal to 0, or IL RL minus of I1 R2 plus of IL R2 is equal to 0, or I1 R2 is equal to IL into bracket R2 plus RL, or I1 is equal to IL into bracket R2 plus RL divided by R2. Call this as equation number 2. From equations 1 and 2, IL into bracket R2 plus RL bracket complete into bracket of small r plus R1 plus R2 bracket complete divided by R2 minus of IL R2 is equal to E, or this equation can also be written as IL into bracket of R2 plus RL bracket complete bracket of small r plus R1 plus R2 minus of R2 square divided by R2 is equal to E, or IL into bracket R bracket of R2 plus RL bracket complete plus R1 into bracket R2 plus RL bracket complete plus of R2 into bracket R2 plus RL bracket complete minus of R2 square is equal to ER2, or IL into bracket small r R2 plus small r RL plus R1 R2 plus R1 RL plus of R2 square plus of R2 RL minus of R2 square is equal to ER2, plus R2 minus R2 plus R2 square minus R2 square get cancels. I1 in IL into bracket R2 bracket of small r plus R1 plus of RL into bracket small r plus R1 plus R2 bracket complete is equal to ER2, or IL is equal to ER2 divided by R2 of R2 into bracket small r plus R1 bracket complete plus of RL into bracket small r plus R1 plus R2. Therefore, IL is equal to ER2 divided by, now take the small r plus R1 outside the bracket, R plus R1 into bracket R2 plus of RL into small r plus R1 plus R2 divided by small r plus R1. Now, IL is equal to ER2 divided by small r plus R1 bracket complete into RL bracket of R2 divided by RL plus of small r plus R1 plus R2 divided by small r plus R1, or IL is equal to ER2 divided by bracket of small r plus R1 bracket complete into RL, R2 divided by RL plus of R plus R1 plus R2 divided by R plus R1. Now, the above equation can also be written as IL is equal to ER2 divided by bracket of small r plus R1 into RL into R2, bracket of 1 divided by RL plus of small r plus R1 plus R2 divided by R2 into bracket small r plus R1. Therefore, VAB is equal to IL into RL. VAB is equal to ER2 RL divided by bracket of small r plus R1 bracket complete RL R2 bracket of 1 by RL plus of bracket small r plus R1 plus R2 divided by R2 into bracket small r plus R1. RL R2 RL R2 get cancels. VAB is equal to E divided by R plus R1 into bracket 1 by RL plus of R plus R1 plus R2 divided by R2 into bracket R small r plus R1 bracket complete. Therefore, VAB is equal to E divided by R plus R1 whole divided by 1 by RL plus of R plus R1 plus R2 divided by R2 into bracket R plus R1. Call this as equation number 3. Now, replace the EMF with its internal resistance, small r. If R is the equivalent impedance or resistance, then 1 by Rn is equal to 1 by R plus small r plus R1 plus of 1 by R2. Therefore, 1 by Rn is equal to small r plus of R1 plus R2 divided by R2 into bracket R plus R1. Call this as equation number 4. Now, remove the load resistance, connect a short circuit between the two terminals A and B. Now, I is equal to E divided by R plus R1. Because AB is a short circuit, therefore no current goes through the R2. Therefore, or call this as equation number 5. Therefore, from equations 3, 4 and 5, VAB is equal to E divided by small r plus R1 whole divided by 1 by RL plus of small r plus r1 plus r2 divided by r2 into bracket small r plus r1. Therefore, VAB is equal to I divided by 1 by Rn plus 1 by RL. Hence, the Norton's theorem. Procedure steps to find the Norton's equivalent circuit. Remove the resistance, if any, across the two given terminals. Put a short circuit across them. Second one, compute the short circuit current I. The third step is remove all voltage sources but retain their internal resistances. Fourth step is calculate the Norton's resistance Rn of the network as looked from the given terminals. Fifth step, connect I, a constant current source, in parallel with Rn between the given terminals. Then VAB is equal to I divided by 1 by Rn plus 1 by RL. Now, in this session, we have learned the Norton's theorem, Norton's statement, proof of Norton's statement, measuring short circuit current I is equal to E divided by R plus R1, measuring Norton's resistance Rn by 1 by Rn is equal to R plus R1 plus R2 divided by R2 into bracket small r plus R1. Replace the entire network by a single current source in parallel with a single resistance. Calculate the voltage across A and B by VAB is equal to I divided by 1 by Rn plus 1 by RL. Depending on this session, we have some questions. Question number 1. The Norton's current is the options are open circuit current, B, short circuit current, C, open and short circuit current, D, neither open nor short circuit current. The correct answer is short circuit current. Question number 2. Norton's resistance Rn is found by, the options are A, shortening all voltage sources, B, opening all current sources, C, opening all voltage sources and shortening all current sources. Option D, shortening all voltage sources and opening all current sources. The correct answer is shortening all voltage sources and opening all current sources. Question number 3. Norton's theorem is true for, the options are A, linear network, B, non-linear network, C, both linear and non-linear network, D, neither linear network nor non-linear network. The correct answer is linear network. Question number 4. Norton theorem cannot be applied to non-linear circuit, B, active circuit, C, linear circuit, D, passive circuit. The correct answer is non-linear circuit. Question number 5. Norton theorem is dash Thevenin's theorem. The options are A, same as, B, converse of, C, cannot say, D, none of the above. The correct answer is converse of Thevenin's theorem. Question number 6. Can we use Norton's theorem on a circuit containing BJT? The options are option A, no, option B, yes, option C, depends on BJT, option D, insufficient data provided. The correct answer is no. Question number 7. Applications of Norton's theorem to a circuit yields. The options are A, equivalent current source and impedance in series, B, equivalent current source and impedance in parallel, C, equivalent current source, D, equivalent impedance. The correct answer is equivalent current source and impedance in parallel. Question number 8. In Norton's theorem, we measure option A, voltage, option B, current, option C, both A and B, option D, neither A nor B. The correct answer is current. Question number 9. In Norton's theorem, we calculate the option A, voltage, option B, current, option C, both A and B, option D, neither A nor B. The correct answer is voltage. Question number 10. Which of the following is also known as the dual of Norton's theorem? Option A, Thevenin's theorem, B, superposition theorem, C, maximum power transfer theorem, D, Millman's theorem. The correct answer is Thevenin's theorem. The reference for the above sessions are Fundamentals of Physics by Halliday, Resnick, Walger, 2002 edition, Principles of Electronics by V.K. Mehta, Rohit. Thank you.